Sorry about that. Thank you, everyone. Yeah, before I get started, I want to talk a little bit about why I see battery research as a really important area that we should be focusing on. So this is a picture of Los Angeles on a particularly poor air quality day. And a lot of this pollution comes from fossil fuel generation and of energy for our electricity grid, and then also from transportation from internal combustion engine vehicles. And climate change has been closely linked to energy generation from these sources, and with a changing climate comes new risks to our food supplies, changing ecosystems, and then also more extreme weather events. And so I think this is something that we want to avoid in the future, and so we need to really transition from fossil fuel-based generation for the majority of our electricity to renewables, which require energy storage technologies to be enabled. Additionally, this problem is not going to go away by just using less electricity. As a planet, we used about 575 quads or quadrillion BTUs. That's 1 million billion BTUs of energy. So it's a really huge number. And it's just predicted to go up. So by 2040, we'll be at about 700 quads. So we really need to think about new ways to generate and store electricity. Additionally, let's say you don't care about climate change and the future of our planet. Maybe you care about your own health. So about 90% of the world's population lives in a place that has air quality below World Health Organization standards. And this poor air quality has been linked to about 7.6% of global deaths. So people are dying just because we have poor air quality due to fossil fuels being used to generate our electricity and our transportation. So with that, what's the alternative? And wind and solar are really two great options for generating electricity in a renewable manner. Right now, they're actually starting to become cost competitive with new coal-fired plants and some new natural gas plants, depending on where you're at in the world. But unfortunately, the intermittency of sun and wind causes these to need storage as well, so that we can maintain the level of grid that we enjoy today. And then electric vehicles are also an opportunity to move away from internal combustion engines, but unfortunately right now they're very expensive. So this is a Tesla Model S. Sticker price is 70 to 90K, and actually most of that cost comes from the battery. So about half the price of the car, a little bit more, is just from the lithium-ion cells that you have on the base plate of the car. So this is the entire bottom of the vehicle that just drops out. It's about 8,000 individual cells. That gives you a driving range of 260 to 300 miles. And so when we think about storing on a grid scale, we need really big batteries that store energy for a long time and are very reliable and cheap. And then for improving EV penetration, we really need to bring the cost of these cars down. Most people can't afford a $70,000 vehicle, and so when you think about how to reduce that cost, you can keep the number of batteries the same, and then you get better value for your money, so you increase the driving range of your vehicle if you have higher energy density, or you can just use less cells, and then that's where the cost of the cars come down and make them more accessible to more consumers. So DOE has set some targets, and they're right along these lines. The first one being low cost of these batteries, about 125 kilowatt hours is the target. Right now we're sitting around 200, 180, something like that. Additionally, you want high energy density, and this kind of goes hand in hand with low cost. So if you have a higher capacity to store charge in your cell costs less because it's a better, you have less of the dead weight that contributes to this cost per kilowatt hour. Additionally, you want long cycling. You don't have to replace your batteries every month or year or something like that. You want them to really go for quite a long time. And then finally, high power, and this is especially important for portable electronics and electric vehicles. You'd love to be able to charge your Tesla up in 15 minutes so you can keep going on your road trip instead of being limited by the range there. When you think about grid scale storage, cost and cycling become really the two dominant parameters. Energy density is not so important because you have a lot of space on some utility land that you have, and then high power you don't need as much for grid leveling as well. So we can look at all the different materials that are available to improve these numbers. On the cathode side or the positive electrode side, you can think about moving to sulfur as an active material. Also these high nickel metal oxides you can work with. Additionally, lithium air, so that's using just pure oxygen as a cathode, turning it into lithium oxide or lithium peroxide. That works. Then on the electrolyte, so this is the separator part that is ionically conductive but electronically insulating. You can look at new liquid electrolytes or new solid state electrolytes, and those can be polymers or ceramic materials to stabilize things there. And then finally the anode, and that's what I'll be talking about today. Two really promising materials are lithium metal and silicon, and both of them are very high capacity, but unfortunately with that high capacity comes a lot of issues that need to be solved before they can be commercialized. So if you're not familiar with how a battery works and what the structure is like, here's a blown up picture of the inside of the material, or the inside of the device. This is the cathode or the positive electrode, as I mentioned before. You have a mixture of some active material, that's again this metal oxide, your sulfur, your oxygen, a conductive additive, generally just some carbon, and then a polymer binder that helps you to hold everything together. You coat it on your metal current collector. Then you have your separator, so this is either some sort of porous inert material that you fill with a liquid electrolyte or a solid lithium ion conductor. And this is really the key to making the battery work. So this is an ion conductor, but it's electronically insulating, and so when you have high energy electrons and lithium ions here, they want to go to your cathode during discharge, but because the electrons can't move through this separator, they're forced to go through the external circuit, and that's where you get the work. And then the anode is similar to the cathode. You have an active material, carbon and binder for silicon, and then lithium metal is actually just a pure lithium metal plate that you'll have on your current collector there. We can look in a little bit more detail about what exactly we get when we move to these different material systems. So here's kind of more traditional battery materials that you may be familiar with: lead acid in your car, NiCad or nickel metal hydride in your old rechargeable, whatever you had maybe 10, 15 years ago. Lithium ion is really, really popular. That's what's in all of our cell phones, all of our laptops nowadays. If you were to just take traditional lithium ion materials and then switch the anode to either silicon or lithium metal, that gets you up to here, which is already quite an improvement. And then when you switch the cathode side paired with lithium metal to metal air or a metal sulfur battery, we can actually start to even approach gasoline level energy densities. These are theoretical numbers, so obviously we have a long way to go before these technologies can reach this, but it shows, I think, the promise of these technologies and why they're worth studying. So that brings me to what I'll be talking about today. I'll start with talking about our self-healing binder that we used for stabilizing the particle fracture of silicon electrodes, and then I'll move into explaining how we used this material to stabilize lithium metal. So we use it as a coating, and then finally I'll end with telling you a bit about some fundamental understanding that we've gained from studying these coating materials on the lithium metal. So in more detail, why is silicon an exciting material to be studied? Well, one, it has very high theoretical capacity. It's about 10 times that of graphite, which is used commercially today. It's also really inexpensive and highly abundant, so it's all over the place. And then there's also a large infrastructure for producing high-grade silicon for the semiconductor industry, and you can actually use the waste from that industry for these battery materials. So the particles that come off when you cut wafers for computer chips can be used here. Unfortunately, and the reason we're not already using it today in high quantities is because it has extremely large volume change. So silicon goes from just pure silicon, and it forms an alloy with lithium with about 3.5 lithiums per every silicon atom. But when it does that, it also goes about a 300% volume expansion. And since silicon's not really an elastic or ductile material, it expands and then fractures. It's quite brittle, and it has anisotropic expansion along different crystal planes. And so what happens is when you lithiate the silicon, it will expand and then fracture, and then you end up having two main failure mechanisms from this fracture. The first is you have all of this new surface area of these smaller particles. Because of the low potentials of the silicon electrode, the electrolyte will react at those surfaces, and that consumes lithium and consumes silicon and increases the impedance of your cell, lowering the performance. And then additionally, you have particles that become electronically and ionically isolated. And what that does is you lose their capacity. They either stay charged or stay discharged, and so your capacity fades from that mechanism as well. So any attempts to stabilize silicon really need to address this particle fracture and particle isolation issue. To that end, there's been a really large amount of study in this area from a lot of different perspectives. One of the main ones, and I've talked with some people who are working on this here today, is using nanostructures. So when you go below about 150 nanometers in a critical dimension, your silicon actually stops fracturing, and it expands and contracts reversibly. And so when you have this nano size, you can keep the particles from failing. Unfortunately, and the main issue with this approach is that these nanostructures can be quite expensive and difficult to synthesize, and so the main challenge in this area is scaling up these processes and making them amenable to producing tons and tons, literally tons, of these battery materials. Another approach that's quite popular and shown quite high performance is to have some sort of carbon coating around your silicon active material, and what that does is that protects the silicon as it fractures, and so you kind of have a you end up with a secondary particle of fractured silicon inside a carbon cage. And that allows all of these fractured silicon parts to maintain their electrical connection and protects the new surface from solid electrolyte interface formation, because that happens actually at the carbon interface that doesn't change over time. Additionally, I'm a polymer person, so I like to think about, instead of doing these nano-engineering approaches, how can we use polymer materials to stabilize cheap and expensive particles? Binders have been a really popular approach to that. So I mentioned earlier you have active materials, conductive carbon, and then your polymer binder. Really, polymers are highly tunable and highly variable, and so there's a lot of opportunity to change the chemistry of that binder and understand how that stabilizes the silicon materials. And so hydrogen bonding polymers have been an extremely successful and popular approach to this. Carbohydrates specifically, and then acid polymers have been very, very successful. And what happens, the reason these work so well is because you have the hydrogen bonding groups of these polymers associate with the silicon surface, and so they maintain strong connectivity of the particles with the carbon in the current collector. And then finally, so that's more of a secondary cross-linking effect or a physical cross-linking. You can also covalently cross-link these polymers, and then you have an elastic binder material that leads to very high mechanical stability of your electrode, and these have also been shown to have quite good cycling performance. So that brings me to our approach, and this was something that had been getting started when I was starting my PhD in the group, and so I was really excited to look at this mechanism in a bit more detail. But essentially, when you have a traditional binder, generally the mechanical properties are fairly rigid, fairly brittle, and so as silicon expands, it doesn't do a good job keeping the particles together, nor does it maintain any sort of conformal coating or connectivity between them. But we used a self-healing binder, and I'll talk about that in just the next slide, that was able to maintain a conformal coating of the polymer over these particles as they fail. And so you maintain electrical and ionic connectivity of these materials as they're cycling and fracturing in situ. And so with this retained contact, you're able to maintain the cycling stability for much longer with large, cheap particles. So we chose a self-healing hydrogen bonding polymer. It is basically these dimer and trimer structures that self-associate via urea bonds into this polymer network. It has a non-polar core that gives us a very low glass transition temperature, which allows for dynamic motion of these hydrogen bonds at room temperature. So we get fully autonomous self-healing at 25 C. Additionally, because these are hydrogen bonds, they're completely dynamic, and the self-healing capability is completely repeatable. So it can happen as many times as you need it to, and this network is actually dynamically rearranging all the time. And then, as I mentioned before, these hydrogen bonding groups have strong association with the silicon surface. And so you have strong interactions with the particles that, again, help to maintain the connectivity of these electrodes. So here's, if you're not used to looking at these plots, this is specific capacity. So this is how many electrons we were able to put in per weight of silicon versus cycle life. So we just charge it up and discharge it and see how much we get out. And then the C numbers are just different rates. So C over a smaller number is faster, C over a bigger number is slower. And we're able to cycle these very large silicon particles. You'll remember I mentioned earlier that 150 nanometers is kind of a critical dimension for silicon to have stable cycling. But you would really like to have very large particles because they're much cheaper to buy, much easier to put into these electrodes. And so we were able to, for the first time, really show successful long-term stable cycling with micron-sized particles using the self-healing binder concept. But what wasn't clear when we were at this point in the study was exactly what was going on. So we had this idea that we thought it was self-healing, and we thought this polymer was really giving us something unique to stabilizing these electrodes, but we didn't really understand exactly what about this polymer was enabling this effect and why it was working so well. And so that's where I'll start talking about what I started doing to really understand some of the fundamentals of What about these mechanics are influencing the stability of these electrodes, and how can we understand what are the key properties so that we can start designing new and improved materials to really open up this parameter space to have these commercialized. So this brings us back to the diagram of the self-healing polymer. As I mentioned, it's mostly this diacid material that we start with, so it gives us a difunctional hydrogen bonding group, and you can imagine this associates with other ones to form mostly linear chains. But then we add in a little bit of this trifunctional group, and what that does is it allows us to form this network, and that gives us our mechanical structure. So we have a gelled material that then behaves a little bit more elastically than just a purely linear polymer. But what we can do is we can change the ratio of these two, and we can go all the way up to about 70% of this trifunctional material, giving us very, very different mechanical properties without changing the chemistry at all. And so this allows us to probe with high precision the mechanics, but again, without changing the chemistry in any way. To probe the mechanics and really quantify what we were doing by changing these crosslinker amounts, we turn to rheology. And so if you're not familiar, you just stick the material between two plates and you oscillate one of the plates while you measure the stress or the strain, depending on what you're pushing. And the plots end up looking like this, so you can use different frequencies of that oscillation at small strain. And the open squares here are the loss modulus, that's the liquid-like properties of the material, whereas the closed circles are the storage modulus or the solid-like properties of the material. So you can see at low frequencies or slow times, we're actually getting a material that behaves like a liquid, so it's flowing. And we see that because we have the loss modulus dominating over the storage modulus. And then as we go faster and faster, we reach a crossover point, and then finally it starts to behave like a solid. So at low time scales or long times, this material is flowing, but when we probe it very quickly, it begins to behave like a solid and respond solidly. So we can do that for all of these, and what we see is the crossover point, which is really that characteristic time scale of the material. So when you're probing at that time scale, you have a match between liquid-like and solid-like properties, is moving to longer and longer time scales. So we're getting more and more solid-like materials as we increase the cross-linking. We can also look at stress relaxation. So this, instead of oscillating, we just add a step strain and watch as the stress relaxes, and you can imagine that's really the flowing of the polymer material as it rearranges to relax the stress. And if it was some sort of elastic or structured material, it would maybe store some of that stress in some sort of structure. But here we see the stress is basically relaxing completely, and we can fit this relaxation to some viscoelastic models and extract a characteristic relaxation time. And what that allows us to do is, again, see what time scale these polymer chains are moving around and what time scale these hydrogen bonds are rearranging. So when we look at a comparison between these two methods, we see quite good agreement between the two, and then we also see that we have about 2 orders of magnitude of time scale that we're probing here. So we really have successfully found a study that gives us very different mechanical properties without changing the chemistry at all. And so then jumping right back into the cycling curves, again, this is capacity or charge stored per weight of silicon versus cycle. You can see very quickly that the most cross-linked material, the most solid-like material, has very poor performance. And then if you look a little bit more closely into the data, what you'll find is that relaxation times on the order of about 0.1 second give us the best cycling stability. And so what this tells us is that there's really a balance between the viscous flow of these polymers and the mechanical strength of the material that's really required for the self-healing binder concept to function. So if you have too solid of a material, the binder in the electrode can't self-heal, and it can't repair itself, and it can't maintain cycling stability. But if you have something that's too soft, too flowable, too viscoelastic, you don't have the mechanical integrity to keep your electrode intact. And so with that, we had really, I felt, understood what was going on with silicon, and we turned our attention to lithium metal, which is another high-capacity material. And we wondered, how could we use this self-healing concept to stabilize the lithium metal electrode as well? And so lithium metal, again, has a very high theoretical capacity, more than 10 times that of graphite that's used commercially. Additionally, lithium is really beneficial because it's the reference potential for all of these battery systems, and so it's the lowest potential you could possibly achieve, giving you the highest voltage of a cell, depending on what your cathode is. So you really maximize your energy density when you're using lithium metal as your anode. Unfortunately, lithium has even more disadvantages than silicon it forms these dangerous short circuits, and that's what happens when your Samsung Galaxy catches on fire or your hoverboard catches on fire. It's a short circuit in the battery that then causes very high currents to pass, the temperature heats up, and then your electrolyte catches on fire. And so we really want to avoid these. Additionally, the lithium metal is highly reactive with all of the chemistries that you put inside the battery. And so any surface of the lithium that's exposed is going to decompose whatever it's in contact with. And you get very high surface area lithium structures in most systems. And so you have very low cycling efficiency because a lot of your lithium and your electrons are going to these side reactions that then limit what lithium you can take back out. So in an ideal world, you would have your current collector here, which is copper, and you would plate lithium in a perfect flat single crystalline plate on top of the copper, and then some very thin decomposition layer would form on top of the lithium, protecting the surface and limiting any further decomposition of your electrolyte. Unfortunately, reality is rarely perfect, and so what we actually see is the solid electrolyte interphase, or SEI, breaks down, and the lithium grows through it, and so you have these very inhomogeneous structures that form. They can be moss-like, they can be dendritic, they can be rod-like. There's, depending on the chemistry, a lot of different structures that can form. And then these dendrites can eventually grow through your cell and cause those dangerous short circuits I mentioned earlier. So we want to avoid this sort of structure and really promote as dense of a lithium deposit as we can achieve. To do this, there's been really a wide variety and a lot of activity in recent years of research in this area. One of the most popular, because it's so simple and straightforward, is using additives in your electrolyte. So you can take a standard liquid electrolyte, carbonate or ether-based, typically with your lithium salt, and you can add in some other molecule that will then preferentially decompose on your lithium or perform some other function to change how your lithium is growing on the surface. Additionally, you can coat some sort of hard SEI, so boron nitride or some sort of carbon film, to again passivate that lithium surface and help to control the nucleation growth of the lithium on your current collector. You can also take your current collector and turn it into a 3D structure, and that's what is done here with these lithium hosts and lithium scaffolds. They effectively take some sort of 3D structure that the lithium will then grow on top of, and that can help limit the negative effects of lithium because you have confined spaces that the lithium is growing into, and you get generally dense deposits with these. And then finally, tough polymer and gel electrolytes. The idea here came out of some work from John Newman's group where they found that a modulus of about 7 gigapascals would mechanically suppress a dendrite. And so this motivated a lot of study, people using very, very high modulus polymer materials as electrolytes to mechanically prevent dendrites from penetrating the cell. Our approach is really different than anything that had been done before. We took, instead of a very, very hard polymer electrolyte material, we instead went the opposite direction and went for a very, very soft polymer coating. So we took that self-healing polymer that I showed before in previous slides, and we coated it on the lithium metal electrode here. And the idea is that if we have this artificial SEI, or this polymer coating that's present, and it has very, very soft, very, very flowable mechanical properties, any sort of cracks or pinholes that form in the SEI will be healed over time as the polymer flows into those cracks. And then hopefully we'll have very dense, very uniform deposits under this adaptive polymer coating. And that's what we see. So when we look at cross-sectional SEMs of lithium deposited on copper without the polymer, you can see, as I mentioned before, these mossy or kind of loose lithium structures that form. But when we have the polymer coating, again, this is copper and then the lithium, we see very, very dense lithium deposits. And this is actually very close to the theoretical 5 microns thickness that you would achieve for 1 milliamp hour per centimeter squared of lithium deposited. This also works at higher current rates, so we can go up to 2, 3, and 5 milliamp per centimeter squared, and this is really important for thinking about high power applications, such as electric vehicles. A lot of the approaches to stabilizing lithium metal don't work at high currents, and so we wanted to really check and make sure that high currents were a possibility for our technique. And again, all of these are very close to that 10 micron thickness that you'd expect for, in this case, 2 milliamp hour per centimeter squared of lithium metal. When we were thinking about why exactly we were getting such, they warned me about that, but when we were thinking about why exactly we were getting such dense lithium growth, we turned to the nucleation to understand that. So this is 10% of the lithium that we deposited before, just 0.1 milliamp hour. And then we take it out and we look at the SEM. You can see here, this is copper and then the lithium nuclei or particles that have formed on the copper surface, and they're very sparsely distributed. You see these large patches of copper that are left bare. Whereas when we have the polymer coating, we see highly uniform and much smaller lithium nuclei in the presence of the polymer coating. And so we think that this is really, this nucleation process, control over that nucleation and growth is what's key to controlling the eventual structure of your lithium metal. Looking at the efficiency of these cells, so this is not capacity anymore, but instead coulombic efficiency, so how much lithium we can pull out after we deposit. Ideally be 100%, typically it's not. And you see here, though, we maintain cycling stability for a longer time. This is, the cell begins to die due to buildup of that resistive SEI that forms, and we delay that by about 20 or 30 cycles here with high efficiency. And so this polymer coating really is not only helping to improve the morphology of the lithium, but helping to improve the stability of these cells over time. So we were the first people to do this polymer coating to demonstrate that it was a successful approach. And after we published this paper, there was a lot of work from a lot of different groups on a lot of different polymer structures. You can really, I mean, polymers are nice because they're so tunable and very easy to work with. And so it's relatively straightforward to try a lot of different materials. And there were some really cool designs, some ionomers or some reactive groups that will bond to your surface. Polymers of intrinsic microporosity, just a whole host. This is just a sampling of some of the activity in the area. But really, most of these designs, when you look at them, they're kind of intuitive based. So people think about what would work well, they design a system, and they test it, and if it works well, it gets published, and if it doesn't, it goes in the trash and they try something else. And so what we really wanted to do was to see if we could find some more general guidelines for designing these polymer films. Because if we can have some design rules or some descriptors that people can use as a handle, then we can really open up the space and accelerate the research. And so that led us to doing a few more fundamental studies. And where we started was just kind of back at the self-healing polymer, but understanding the mechanics. So I mentioned before, mechanics are really are thought to be very important for this lithium metal interface. And so what we did was just take this supramolecular hydrogen bonding self-healing polymer and covalently cross-link it here. Instead of the hydrogen bonds, it now has a covalent link, and now it's an elastomer. So instead of a viscoelastic flowable material, it's just a thermoset. And you can see very easily, this is SEM of a large portion of the electrode. Here, it's highly uniform, those small nuclei. But with the elastomer, we see, again, this patchy, poor quality deposition. And so we see that very quickly, the mechanics are really important for the global growth. But when you zoom in on these SEMs and you look at the small particles individually, you see that these look very similar. And so what that tells us is while the mechanics are really important for the global properties of these electrodes, the chemistry is really what's driving the local morphology of the lithium. And so with that understanding in hand, we can choose a wide variety of polymers from a large set of families that have all been used in batteries. So polyethylene oxide is a common polymer electrolyte material. These fluoropolymers are common binders. Polyurethane is another common electrolyte. Here's our two in-house self-healing materials. And then PDMS has also been used as a coating for the lithium metal and has shown some nice performance. And so when we select all of these, we have very, very different mechanical properties, very, very different chemistries, and really covering a lot of parameter space to try and find what properties of these materials are really affecting the lithium morphology. So we can do the same sort of SEM experiment. Again, this is 0.1 milliamp hour per centimeter squared, just a small amount of lithium deposited on the copper surface. Again, the patchy growth on bare copper, the small particles of the self-healing polymer. Polyurethane has these really, really spherical particles. Polyethylene oxide has these kind of rod and random shaped particles. And then the fluoropolymers have very, very large deposits that form. But I spent a lot of time staring at these SEMs, and there's not really any easy, straightforward analogies that you can draw between these different chemistries to understand why the shapes are the way they are. You can also look at the mechanical properties. So these are stress-strain curves. You'll see we have elastomers here. We have plastic materials that are hard and soft. We have these flowable materials that are extremely soft but very highly stretchable. So really a wide range, but again, there's no real correlation here between these. We can look at the viscoelastic properties. So this is rheology and DMA. Again, the frequency response. So we have materials that are linear. In these ranges, we have these viscoelastic materials. Again, harder viscoelastic materials, softer ones, elastomers, just a wide range. But again, there's no clear correlation between these properties and the lithium morphology that we're seeing. And then finally, this is DSC. We have low glass transition temperature materials, highly crystalline materials, totally amorphous materials, but again, no real correlation. So we're looking at all of these polymer properties, but not really finding any sort of correlation between these properties and the lithium morphology. So what we turn to is the thermodynamics of the lithium nucleation process. And this is the free energy of nucleation of just any particle electrochemically. It's a balance between the bulk effects, which are driven by the overpotential of the process, and then the surface effects, which is just governed by the interfacial energy times the surface area. And so you can differentiate this and assume a spherical particle, and that gives you a critical radius of nuclei. So below this, nuclei won't form, and it'll just go back into solution. But above this, you will have a nuclei form and deposit on the surface. And what we see is that, again, this is the interfacial energy, and this is a combination of the lithium surface energy and the polymer surface energy, and then the overpotential, which is just governed by the exchange current via the Toffel equation. And so this gave us a handle to really start to understand what properties of the polymer should we be looking at and trying to understand, to look at this lithium morphology. If we do some scaling analysis, you do a Taylor expansion of this interfacial energy, you can end up that it's linear in the polymer surface energy, and then the exchange current shows up down here in the overpotential. So we started looking at these properties, and then again, this is just the same set of equations that I showed on the last slide. Looking at surface energy versus the average diameter that we take from those SEMs, we see very easily that there's some grouping, but not really a clear trend. And so, unfortunately, surface energy doesn't work, but this one is such an easy one to measure, that's why we started with it. So that means we need to start looking at the exchange current. However, for lithium systems with these coatings, exchange current's not trivial to measure. And so what we have to do is turn to microelectrode studies. The reason that exchange current is pretty difficult to measure for lithium systems is because we want the exchange current of lithium in the presence of the polymer coating. But as I mentioned before, lithium's highly reactive. And so we have to scan very, very quickly to get a pure CV that doesn't have any sort of influence from these electrolyte decomposition products that form. And when you think about the high rates that we need to get a scan that fast, we have to use very, very, very small electrodes to make that achievable with our instrumentation. So this is a 25 micron tungsten electrode, microelectrode, that we scan at 200 millivolts per second. So this whole CV here is acquired in about 4 seconds, which is very fast and almost as good as we can do to prevent any SEI formation and really probe the pure interaction between the polymer coating and the lithium surface. So looking at exchange current density, as I mentioned, that's hard to measure, but fortunately it has a proxy as the dielectric constant of the polymer material. And we understand this as the dielectric constant is really how well the polymer can solvate these ions. And so the exchange between the surface and the polymer coating happens better or more quickly in a high dielectric medium than it does in a low dielectric medium. And this is a relatively straightforward parameter to measure for a polymer, and so we're using this as a descriptor here instead of the exchange current. But again, when we look at just the exchange current density versus the diameter, we can see some clustering, but there's no real clear trend here between these different systems. But maybe you're saying, well, you wouldn't expect that because they're competitive with each other. So you have surface energy in the numerator and then exchange current down here in the denominator. So when we do look at this parameter, there is a bit of a linear trend. And so what we believe we found now is these two descriptors for these polymer coatings. So you can have something that has a very low surface energy and a very high dielectric constant or high exchange current that will then give you larger diameter lithium morphology that then leads to better cycling. To put that in a bit more of a schematic or diagrammatic way, You can see again here that low surface energy and high dielectric constant lead to high interfacial energy and high exchange current, respectively, which gives you larger deposits from that scaling analysis. And then again, high surface energy and low dielectric give you low exchange current, low interfacial energy, which lead to smaller lithium deposits. When we look at the cycling efficiency, and again, this is just how much lithium you can remove after you deposit a fixed amount of lithium, we see that in general, the polymer coatings that give smaller lithium deposits have lower Coulombic efficiency, and the materials that have higher, larger deposits give higher Coulombic efficiency. But unfortunately, this isn't a perfect relationship. Remember, PDMS was really in the middle, and then the fluoropolymers were the largest lithium sizes, and this is because there's also surface reactions that happen that are also very important that we're ignoring here by just looking at the thermodynamics of this process. However, we do have now two very easy to measure properties of these polymer materials that allow you to design new coatings moving forward. So just to summarize, I started off by talking about our self-healing binder for silicon electrodes and understanding the mechanical properties of these binders and what allows them to function as self-healing materials for silicon. Then I talked a little bit about how we adapted that coating to lithium metal, and then ended with the fundamental understanding of these coatings on lithium metal and finding dielectric constant and surface energy as two really key parameters from the polymers in order to stabilize and design better coatings. So with that, I'd like to thank my graduate advisor, Jinan Bao, and Yichue was a close collaborator in all of this battery work. We used a lot of his facilities for all of this. And then Yang Xiaohorn, my postdoc advisor, as well as all of the people in my graduate group and my postdoc group, funding sources, and then these really close collaborators for the work that you saw today. All of them contributed a lot. So with that, thank you and look forward to your questions.